I want you to just close your eyes for a second. Imagine that you are standing on the surface of Mars. You're looking out at this vast, sweeping landscape, right? Red dust, these ancient craters, and this oddly close kind of butterscotch-colored sky.
It's quite the image.
It is. And so you decide to take a step. You push off the ground, and suddenly you are bounding effortlessly into this thin Martian air. Because the gravity there is only, about 38% of Earth's pull.
Right, less than half.
Exactly. So your movements feel incredibly light, your jumps stretch higher, you hang in the air longer, and honestly, it just sounds like an absolute superpower, doesn't it?
It really does. I mean, it's the ultimate playground fantasy, right? It's that highly romanticized vision of planetary exploration that science fiction has been, selling us for over a century now. We imagine becoming these nimble, leaping explorers the exact moment we touch down.
Yeah, but I have to immediately puncture that fantasy. With a very harsh, very quiet biological reality. Because your body, my body, the body of every single person listening to this right now, we were engineered over millions of years of just ruthless evolution for Earth's constant, heavy 1G pull.
We are Earth creatures through and through.
We really are. And when you take that invisible, relentless force away, the superpower fantasy crashes hard into physiological reality.
And it crashes because biology is fundamentally pragmatic. I mean, if an organism doesn't need to expend energy maintaining a physical structure, it just won't.
Right.
Without that constant 1G force anchoring you down, your body immediately starts trying to optimize itself for a lighter world. And in biology, optimizing for a low-gravity environment actually means actively dismantling your own physical structure.
Which is terrifying.
Yeah.
And that quiet, invisible dismantling is the exact focus of our deep dive today. We are pulling from a massive, highly detailed research article titled, "Mars Missions Are Coming, but is the human body ready for its gravity?"
It's a fascinating piece of research.
It really is. So our mission today is to look past the rockets and the rovers, and we want to explore this hidden biological degradation that the human body faces in partial gravity. We're going to unpack a truly groundbreaking orbital experiment that might just fundamentally change how we plan for interplanetary colonization.
Yeah, and it represents a profound shift in the aerospace community, honestly, because for decades, all the funding, all the anxiety, it all went toward the exact same question. How do we get to Mars without dying in transit?
Right, the journey itself.
Exactly. But the data we are looking at today forces us to confront a much more insidious problem, which is what happens to the human machine if we actually stay there?
Okay, let's unpack this, because I think there is a huge misconception out there about how humans actually handle space.
Oh, absolutely.
We see videos of astronauts on the International Space Station, the ISS, floating around doing flips, playing with water droplets, and they seem totally fine.
They look like they're having a blast.
They do. And we know they work out.
Yeah.
We see them strapped to treadmills with these heavy bungee cords. So I think the natural thought process for most people is, well, if you go to Mars, you just pack some heavy resistance bands, you dedicate 2 hours a day to the space gym, and you'll be healthy.
It makes logical sense, sure.
Right. But the source material completely shatters that assumption. It points out that astronauts on the ISS lose massive amounts of muscle tissue despite those rigorous daily exercise regimens.
And we should be clear, the exercise protocols on the ISS are brutal.
Yeah.
Oh, yeah. They are using the Advanced Resistive Exercise device, pulling heavy loads for hours a day. Yet the degradation still happens. And it happens because working out for 2 hours cannot compensate for the fact that for the other 22 hours of the day, the ambient 24/7 structural load of gravity is completely absent.
Wow, so it's a constant deficit.
Exactly. I mean, on Earth, even when you are just standing in line for coffee, your body is actively working against a tremendous amount of physical force.
Which brings up a way I've been trying to visualize this for you, the listener. We tend to think of skeletal muscle just as the things that make us visibly strong. We think of aesthetic things like biceps or quads or, getting a six-pack.
Right, the mirror muscles.
Yes, exactly. But skeletal muscle makes up over 40% of our total body mass. So I want you to think of it less like the pulleys that move your arms and more like the load-bearing walls and the central metabolic engine of a house.
That's a great way to frame it.
Because if you get even a slight crack in that foundational load-bearing wall, it cascades into massive systemic issues for the entire building.
That is a highly accurate analogy, particularly the metabolic aspect, because muscle tissue isn't just, inert meat waiting for a signal to contract. It is an active, metabolically demanding organ. Your muscles are actually the largest sink for glucose in your entire body.
Wait, really? The largest sink?
Oh, by far. They physically pull sugar out of your blood, which regulates insulin. They secrete hormones. They dictate your posture, your bone density, and just your overall biochemical survivability.
So when we talk about muscle loss in space, we aren't just talking about an astronaut getting a little weaker or looking skinnier. We are talking about their central metabolic engine literally stalling out.
Precisely. And the mechanism behind this is something called mechanotransduction.
Mechanotransduction.
Yeah, it is a fascinating biological process. Your cells literally have physical sensors, these proteins that span across the cell membrane.
Little antennas.
Basically. And when Earth gravity pulls on your body, those proteins are physically stretched. That mechanical stretching opens up ion channels, sending a chemical signal straight into the cell nucleus that says, hey, we are under load here. Synthesize more protein to keep these walls strong.
Okay, so the stretching is what keeps them building.
Yes. So take away gravity, the stretching stops, the channels close, and the body immediately sends in scavenger proteins to break down the muscle for spare parts.
Which is frankly terrifying when you apply that to a Mars timeline. I mean, a trip to Mars is not a quick sprint to the moon.
Not at all.
You're talking about 7 to 9 months in zero-gravity transit just to get there. And then a long-term stay on a planet where the resistance pulling on those cellular sensors only weighs 38% of what it did on Earth.
And that brings us to the core scientific dilemma that this research actually tackles. We already know from the ISS that microgravity is actively destructive. So the natural pressing question becomes, is the partial gravity of Mars enough to save us?
Right. Is 38% enough to trigger those sensors?
Exactly. Is it enough to physically stretch those cellular sensors and keep the load-bearing walls up? Or does the house still collapse, just, a little bit slower?
But testing that is a nightmare, right?
Yeah.
I mean, you can't just send a multi-billion-dollar crew to Mars, cross your fingers and say, hey, call us in a year and let us know if your metabolic engines have melted down.
No, you cannot.
You absolutely need hard data beforehand.
And what's fascinating here is how researchers actually managed to extract that data without ever leaving low Earth orbit.
Oh, this is the best part.
Right. An international team of scientists designed an incredibly complex, highly controlled orbital experiment. They basically sent a specialized habitat module into space, aboard a laboratory, and this module was equipped with its own internal centrifuge system.
I want to pause on that for a second because that just sounds like an absolute engineering headache. To be clear, we are talking about putting a spinning metal machine inside a space station that is already floating in microgravity.
Yes.
Doesn't spinning a centrifuge generate massive vibrations that would destabilize the entire space station's orbit?
Oh, it's an immense technical challenge. If the centrifuge is even slightly unbalanced, it acts like a washing machine with a brick in it.
Oh, wow.
Yeah, it would transfer all that kinetic energy right into the walls of the space station. So they had to design these active vibration dampening systems and counter-rotating balances just to make this experiment possible.
That's wild.
But they had to do it. Because by spinning the centrifuge at precise speeds, centrifugal force pushes the subjects against the outer wall of the habitat. And this perfectly simulates different levels of gravity right there in orbit.
That is so clever.
And for this, they used mice as their biological proxies.
Okay, so let's look at how they structured this, because the experimental design is what actually yields the answers we need. They exposed these mice to 4 distinct gravitational conditions for 28 days in orbit, right?
Correct.
So group 1 was left in ambient microgravity near zero, just floating like a standard ISS astronaut.
Exactly.
Group 2 was placed in the centrifuge and spun at 0.33 G, which the source says is designed to very closely mirror the 0.38 G of a Martian surface.
Right, the Mars proxy.
Then group 3 was spun at 0.67 G, and group 4 was spun fast enough to simulate a full 1 G, so a perfect recreation of Earth gravity.
And that fourth group, the 1G group in space, is arguably the most important part of the entire experimental design.
Wait, why is that? I assumed we already know exactly what 1G does to a mouse because we have billions of them running around here on Earth. Why go through the massive expense of flying a 1G control group all the way into space?
It's a fair question. But it's because spaceflight introduces a whole cocktail of extreme biological stressors that honestly have nothing to do with gravity.
Like what?
Well, you have the violent bone-rattling vibration of the rocket launch itself. You have elevated cosmic radiation. You have the psychological stress of a highly confined environment.
Oh, I hadn't thought about that.
Right, so if you just compare a floating space mouse to a mouse sitting in a comfortable lab in California, you don't know if the muscle loss is from zero gravity or from the stress of the launch and the radiation.
Oh, okay.
By putting a 1G control group in space, you isolate gravity as the single independent variable. Every mouse experienced the launch, the radiation, the confinement. The only difference was the spin of the centrifuge.
That makes total sense. You strip away the noise to look only at the gravity.
Yeah.
So they took microscopic baseline measurements of all these mice, spun them in a space centrifuge for almost a month, and then brought them back down to Earth.
Yes.
So here's the multi-billion-dollar question. Did that Mars-like gravity, that 0.33 g spin, act as a biological shield? Did it keep those mechanotransduction sensors stretched enough to protect the house?
The entire aerospace medicine community was holding its breath for this data, because if 38% gravity is enough to maintain a human baseline, then colonizing Mars is just an engineering problem.
Right.
But if it's not enough, it becomes a fundamental biological crisis.
Here's where it gets really interesting, and honestly, a little grim, because the results of that 28-day orbit were deeply mixed. The data showed that the Mars-like gravity, the 0.33 g condition, did significantly reduce muscle loss when compared to the mice floating in microgravity.
Okay.
So yes, it offered some physical protection, but it did not completely prevent the muscle atrophy. The breakdown still happened.
It slowed the bleeding, but it did not stop the hemorrhage.
Exactly. To bring it back to an analogy, it's like getting a D on a test. It's better than a 0, but you're still failing. Or, it's like trying to power a massive, heavy water wheel using just a tiny trickle of a stream.
Right.
Sure, the 38% gravity provides some resistance, the water's hitting the paddles, but there simply isn't enough pressure, enough kinetic force to keep the heavy metabolic engine actually turning. The machine still slowly grinds to a halt.
That is exactly what the cellular data reflected. The physical tension just wasn't high enough to keep those ion channels fully open. But the researchers didn't just note the failure at the Mars level.
No.
No, they discovered a critical threshold for biological maintenance. That third group of mice, the ones spun at 0.67 g, showed something remarkable.
And that's roughly 2/3 of Earth's gravity, right?
Right. At 0.67 g, the muscle degradation was essentially eliminated. Yeah, at that specific threshold of mechanical load, the biological sensors in the tissue triggered the chemical pathways that said, okay, this is enough weight. Maintain the structural integrity. The muscle mass was actually preserved.
So 67% of Earth's gravity is the magic number for baseline mammalian survival. But Mars is only offering 38%.
It's a problem.
That is a massive deficit. And the source material highlights that the researchers didn't just look at the size of the muscle under a microscope to figure this out. They wanted to measure functional performance, right? Because an astronaut's bicep size doesn't matter if they don't have the sheer grip strength to, say, pull a lever to seal an airlock during an emergency.
Function is everything in space. Everything. So to test this, the researchers evaluated the grip strength of the mice using advanced diagnostic techniques, specifically relying on something called electrical impedance myography.
Okay, I am going to admit I got a little lost in the weeds on this one in the research.
Yeah.
How exactly does electrical impedance tell you how strong a muscle is? Because it sounds like testing a car battery, not biological tissue.
It is actually very similar to testing a circuit. Electrical impedance myography sends a very mild, high-frequency electrical current right through the muscle tissue.
Okay.
What they are measuring is how the tissue resists that current, specifically looking at resistivity and reactance. Because healthy muscle fibers are dense, they're thick, and they're surrounded by intact cellular membranes.
Right.
They force the electrical current to navigate a complex, highly structured maze, which creates a very specific electrical signature.
Okay, so a healthy muscle looks like a dense electrical grid. What happens when the muscle starts degrading in that Mars-like gravity?
Well, when the muscle breaks down, the cells shrink, and the space between the cells fills with extracellular fluid.
And fluid conducts electricity.
Exactly. That fluid is highly conductive. So when you shoot the electrical current through atrophied muscle, the current just bypasses the cells entirely and shoots straight through that watery extracellular fluid. The electrical resistance plummets.
That is brilliant.
It gives you a highly accurate, functional map of the tissue's internal health and structural integrity, completely independent of its physical size.
They aren't just taking a tape measure to the muscle, they're testing the actual internal wiring.
Precisely.
And the grip strength data from these electrical tests perfectly mirrored the mass data. At the higher 0.67 G level, the muscle's electrical grid remained highly structured and stable. But at the Mars-like levels, that functional performance actively declined. The wiring was falling apart.
But the researchers took it even further. They moved away from the physical muscles you can see and flex, and they went looking for the invisible systemic damage. They analyzed the blood plasma of these subjects, searching for the metabolic exhaust of this muscular breakdown.
Because if the body is actively eating its own muscle tissue for spare parts, that waste material has to end up somewhere, right? It gets flushed into the bloodstream.
Precisely. The researchers utilized metabolomic profiling and identified 11 specific metabolites that drastically change concentration depending on the exact level of gravity exposure.
11 of them.
Yeah, we are talking about highly specific biomarkers here. For instance, they found elevated levels of things like 3-methylhistidine.
What exactly is 3-methylhistidine?
It's an amino acid derivative. Your muscle fibers are primarily made of two proteins, actin and myosin. When your body decides it no longer needs a muscle-like when it's only experiencing 38% gravity, it breaks those proteins down.
Okay.
When actin and myosin are destroyed, 3-methylhistidine is released directly into the blood. The body cannot reuse it, so it just floats in the plasma until it's excreted.
So a spike in that specific amino acid in the blood is undeniable, chemical proof that your skeletal walls are actively being dismantled. It's not a theory. It's happening right then and there.
Exactly. They also found significant alterations in lipid peroxides, which are markers for severe oxidative stress.
Oh, wow.
Yeah, so the cells aren't just shrinking, they are chemically stressing and damaging their own lipid membranes in the low-gravity environment. These 11 metabolites serve as a real-time chemical map of exactly how the organism is failing to adapt.
I think of these 11 metabolites like the check engine lights on a car dashboard. For you, the listener.
Yeah.
You know, you are driving down the highway, the car feels fine, the steering is responsive, but suddenly that little cluster of orange lights flicks on.
Right.
It's a hidden biological signal telling you that something deep inside the engine block is fundamentally failing, even if you haven't felt the car slow down yet. Could we use these specific biomarkers to monitor astronauts in real time on Mars? Literally running daily blood panels to catch the damage before the astronaut even realizes they are losing strength.
That is exactly the medical implication here. In aerospace medicine, proactive monitoring is everything, because once structural degradation crosses a certain threshold, once bone density drops too low or the metabolic engine stalls out too far, repairing it in a low-gravity environment is virtually impossible.
Yeah, you can't just send them to a rehab clinic.
Exactly. If mission control can monitor these 11 metabolites continuously, they can see the biological foundation cracking on a molecular level weeks before the astronaut actually fails a grip strength test.
So what does this all mean? We have a situation where the biological data is literally screaming at us that 38% gravity is simply insufficient to maintain human physiology. The water wheel just doesn't have enough pressure to turn.
Right.
That means the entire paradigm of how we plan for a Mars colony has to shift dramatically. We can't just land the ship, plant a flag, build a dome, and assume the planet's gravity will take care of the rest.
The paradigm of passive survival has been completely shattered by the centrifuge data. It proves that the destination is just as biologically hostile as the journey.
And the source material lists out specific heavy-duty countermeasures that are no longer just sci-fi concepts, but absolute non-negotiable requirements if we want people to live on Mars for years at a time. They talk about artificial gravity habitats. We might literally need to build sleeping quarters that act as short-arm human centrifuges.
Imagine that.
Right. Physically spinning the astronauts around for 8 hours a night just to give their cellular sensors a dose of 1G pressure.
Which turns a stationary Martian habitat into an incredibly complex moving machine, increasing the risk of mechanical failure exponentially.
Right. And beyond the engineering, they mention intense pharmacological interventions. If the physical mechanical pressure isn't there to open those cellular ion channels, we're going to have to design new drugs like myostatin inhibitors that chemically trick the cell into thinking it's experiencing heavy gravity.
Exactly.
We have to artificially force the body to keep synthesizing protein, bypassing the mechanotransduction process entirely.
If we connect this to the bigger picture, This research redefines the timeline and the cost of interplanetary colonization. Space agencies have historically viewed Mars as a somewhat safe harbor. The terrifying part was the transit, dodging solar flares and surviving the psychological isolation of deep space.
Just surviving the trip.
Exactly. But this data proves that the Martian surface is not a safe harbor. It is a slow, insidious environment that will quietly dismantle human biology if we aren't constantly, aggressively fighting back with centrifuges, engineered drugs, and continuous metabolomic blood monitoring.
It turns a mission of exploration into a perpetual medical intervention.
This raises an important question, and it's one that moves us from the realm of pure biochemistry into something much more existential. As we established right at the beginning of this deep dive, evolution shaped every single cell, every membrane, every metabolic pathway in our bodies under the constant, unrelenting force of 1G.
Yeah, we are literally creatures of Earth's gravity.
We are.
It is the invisible architect of our entire physiology.
Exactly. So if 38% gravity isn't enough to sustain a healthy, fully grown adult astronaut who had the benefit of developing on Earth, what happens to the future generation? Right. What happens to the skeletal structure, the cardiovascular system, and the internal wiring of the first child ever born on Mars? Without the mechanical trigger of Earth's gravity to guide their development, their bodies will grow in ways we cannot even begin to accurately predict.
That's a profound thought.
They might survive, sure, but their biology would be fundamentally, perhaps irreversibly, altered. They would no longer be biologically attuned to Earth.
Which brings us right back to that image we started with. When you finally stand on the surface of Mars, looking out at that ancient red landscape, and you take that first bounding superpower step into the air, the biggest challenge you face won't be the immense rockets that got you there, or the complex rovers you drive.
No.
It will be your own cellular biology, silently fighting against a world it was never designed for.
A world that lacks the fundamental force required to keep the house standing.
So, as we look toward the future and we talk about colonizing a new world, you have to ask yourself a very serious question. As a species, will we figure out a way to artificially engineer the Martian environment, spinning habitats and gravity beds, to perfectly suit our earthbound bodies? Or ultimately, to survive out there in the dark, will we be forced to permanently modify our own biology, completely redefining what it even means to be human?
It may be the ultimate test of human adaptability.
It really is. Thank you for joining us on this deep dive into the hidden realities of Mars gravity. Keep questioning the universe around you, keep looking for the hidden signals, and we will catch you next time.